Okay, so the next problem we'll be doing is this one over here, which is basically, this is a Venturi system, and this is kind of similar to the manometer problems we did. We're going to follow exactly the same procedure. But before we start this problem, let's just recall the general procedure, which is step 0, read the problem statement, do a figure sketch, summarize the input and output. So step 1, diagram figure that will be used to write down the equations. So step 2, we write down the main solving equation or equations. That most of the case will be coming from one of these equations. If we can solve the problem at this step, we jump directly to step number 4. Otherwise, we need to find additional equations until the number of equations matches the number of unknowns. Okay, so let's just get started following that procedure. All right, so this is the problem we're going to be solving. So that's step number 0. Basically, in most cases, it's just a matter to redo the figure. Okay, so let's just redo the figure very quick. So here it looks like we're going to have one tube over here, another tube somewhere lower over here. All right, and looks like we're going to have here a pipe, the pipe, which is going to go down to this one, and then this one is going to go back. All right, we need to do the center line, so let's say that our center line will be somewhere over here. So this will be point lowercase a, and this will be point lowercase b. All right, we could leave it just this way, but this go down to this, and then it's going to go back. All right, and what happens, so here we have a fluid that is higher here, will be lower over here. All right, so let's see. They're telling us that the change in height between this point here and this point here is L. Okay, and the substance going inside the Venturi over here is kerosene with a specific volume. If you remember, the term specific means always per unit mass of 0.00122. So actually here it looks like they did a mistake because the unit should be cubic meters per kilograms and not kilograms per unit, not kilograms per cubic meter. All right, so let's read the problem statement now that we have the figure. So liquid kerosene flows through a Venturi meter. Okay, so the Venturi is to measure the difference in pressure between 2 points. The pressure of the kerosene in the pipe supports columns of kerosene that differ in height by 12 centimeters. So basically that means that L over here equal to 12 centimeters, which is what? 0.12 meters. Okay. Determine the difference in pressure between point A and point B. So what we need to do here is to find delta PAB, which will be basically PB minus PA in kilopascals. Does the pressure increase or decrease as the kerosene flows from point A to point B, as the pipe diameter decreases? Okay. The atmospheric pressure, so the atmospheric pressure that will be acting over here, but as well over here, is equal to 101 kilopascals. The specific volume of kerosene is, so here they have it correct, the units, but wrong on the sketch. So it's 0.00122 cubic meters per kilogram, and the acceleration, the gravitational acceleration is equal to 9.81 meter second square. Okay? Alright, so this was step 0. So over here, now we go to step 1. So step 1, I always say, is the most important step. So let's say we're first going to start to go from point 1 over here to point A. So let's do a figure about that. This, and let's just say our point A. Now we'll do the whole figure again. Just say point A will be right here. Okay, this will be our point 1. We know this is P atmosphere. Okay, and let's call all that distance over here H sub A. Okay, so over here, just by looking at this equation, again, we could take one little element and do the summation of forces, but let's follow the procedure we did for the manometer. So what should be the pressure at point A? So we know it should be equal to the P atmosphere, and then either plus or minus rho G H, and in this case would be H sub A. So where is the pressure higher? So here would be P atmosphere, and then on top of A you're going to have all the pressure created by all this fluid on top of it, because this has some weight, okay, that is acting upon point A. So it should be plus rho GH, and let's say this will be expression little Latin 1. Okay, so you see one figure, one equation. Now let's see what would be point B. We can do similar, but now for this type of the figure. So let's say I do this. All right, and let's say our point B should be here. This time this will be G, and let's call here this point 2 over here, 2. But again, we know we have here P atmosphere acting. And now let's look at that distance over here. So okay, so let's say this will be H sub B. So for the same reason as over here, what would you have? PB should be equal to the atmospheric pressure at this point plus all the pressure that is induced by all the fluid in top of point B. So plus rho G HB. And this will be our equation 2. So what are we trying to find? The difference between PB and PA. So if we combine these two equations, so combining the two equations, we're going to get that PB minus PA will be equal to what? P atmospheric plus rho G HB minus P atmosphere plus rho G H sub A. So this will give us what? If you can see right away, this term will cancel this one. If we factor out, we get rho G HB minus H sub A. Okay. So this is really the expression we have, but we see that we don't know H sub A or H sub B, so we cannot really solve. So basically what we need to do now is maybe go to step number 3. So let's wait 1 second. This is step 1 on this side, and really what I've done on this side is step 2 to write down the equations. Okay, the two main equations, and we made it to this equation here. Now let's say step 3, which will be to find additional equations. Okay, so let's look at the figure and see what can we find over here. So if we look at this figure, maybe, yeah, we can do it over here. So if we call this H sub B then we could say what? That H sub A, which is over here, will be equal to what? Should be equal to H sub B plus the distance L. So if I just go back over here and let's say the additional equations will be what? We keep H sub B as H sub B, but now we just say that H sub A equal to H sub B plus L. Okay? So if we substitute into the star equation, what do we have? Difference in pressure AB will be equal to rho G. Let me just rewrite H sub B minus H sub A. This will give you rho G H sub B is unchanged minus H sub A becomes H sub B plus L. So now it's easy to see that the H sub B will cancel out, so that at the end we have that the change in pressure between AB will be equal to minus rho G L. Okay, so now we have everything. We know, oh, not yet. So let's look at rho. What are the units of density? Kilograms, meter cubes. What are the units of the specific volume? Cubic meters per kilograms. So basically, the density is just equal to the inverse of the specific volume. So the above equation, if you want, you can go now to step number 4. And solve, but if you want this time we can just say that delta change in pressure will be equal to minus 1 over V GL. So if we do the numerical application, what are we going to get? So we get minus 1 over 0.00122, and this will be meter cubes per kilogram times G, that will be 9.81 meter per second, times 12 centimeters, that we already say is 0.12 meters. Okay, so if we do this calculation, we get that we get over here equal to 964.92 and the units will be, so let's see, this will be here meter square, so we'll have kilograms on top divided by meter second. Okay, so that's not the units we are looking for. We are looking to get our result in kilopascals. So let me go to the next page and we do some units manipulations. So basically from the previous page we have that our result, our change in pressure, will be equal to negative 964.92, and the units we have are kilograms meter second. Okay, so let's see, how can we do this? So we need to get pascals. So what is a pascal? Is newtons meter square, and we know that a newton will be kilograms meters per second divided by meter square. So really 1 pascal is 1 kilogram divided by meter second, which is what we have over there. Okay, so we could say right now that delta PAP equal to negative 964.92 pascals. Now if we want kilopascals, what do we need? So 1 so we'll have actually, so 1 kilopascals will actually be equal to what? To 1,000 pascals. That way you see this one will cancel this one. So at the end what we have is that the change in pressure will be equal to negative 0.965, if you want, kilopascals. So in the problem they are also asking us that what is the meaning, or what is the change in pressure between A and B as we go through the flow. So does the pressure increases or decreases as the current flows? So the negative sign means that actually the pressure is decreasing as we go from point A to point B. Okay, so we can say the negative sign indicates a decrease in pressure between point A and B. Okay, so this will be the end of the problem.